All right. So what we've got, this is going back to unit 3 with scatter plots and least squares regression lines. We've got this regression equation given to us. It says the predicted winning percentage of a team is going to be 44 plus 0.0003 times the attendance. And the attendance is given in this case, we have an attendance of 34,000. So it's pretty straightforward. I'm just going to put, I'm not going to write the full thing. I'm just going to put the predicted W, winning percentage. In this case, it's going to be 44 plus 0.0003 times 34,000. So we want to predict what the winning percentage should be. And when we do this, my math was correct. I got 54.2% is the predicted winning percentage. And now the question is, what's the residual? So if the actual winning percentage is 55%, that's pretty close. You know, you can't get much closer than that. So if it's 55%, then I can just take that 55%. Remember, your residual is always the actual minus the predicted. And it's important to keep the actual first. So that's going to be 55 minus 54.2. Of course, we're looking at the percents there. You could write it in decimal form. And you'll end up with 0.8. So 0.8%. And there it is. It's a positive one, C. So there we are. That's the whole idea of that particular bell work. So we're going to be looking at random variables. And when we left off, I just want to remind you, we were looking at transforming random variables where we can add a constant. And maybe just as a brief review, if you have a random variable x, or an expected value of this, when you add a constant to it, so if you have the expected value of x plus some constant, that's the same as just the expected value that you had to begin with plus the constant. So you don't need to do any complex calculations here. The standard deviation, whenever you have a random variable plus a constant, is just the same as it was before. It's the original standard deviation. Now, if you are multiplying, so your expected value is going to be multiplied c times x, then that's the same as c times the expected value. And lastly, if you have the standard deviation of some, if you have the standard deviation of it, a constant multiplied by your random variable, then it's just going to be, the standard deviation is going to be c times the standard deviation of x. So that was the main idea. One thing that we also talked about was this idea of variance. So the variance is just your standard deviation squared. So that doesn't change when you add a constant, but it does change in this way when you are multiplying. So you're going to have c squared times your variance, your original variance. And this is all from the notes on Friday. I just wanted to give a brief reminder of that because that's going to come into play. Now, where we specifically left off was we were running into some problems where I told you if you tried some of those problems in the book over the weekend, you might have had a problem where it says something like 3 times x. And you might have just used this idea. Well, I'm going to multiply 3 times the expected value. That worked out just fine. No problems there. But then you tried 3 times the standard deviation. You check the answer in the back of the book and it's not right. We're going to talk today about why that didn't work out. Okay. I guess maybe I should stop there. Any questions on this recap? You good with where we're at? Okay. Then let's move forward. This is not adding and subtracting a constant to a random variable. This is adding and subtracting random variables themselves. So if you have 2 random variables, what do we do when we want to combine them? Well, we're going to do this with a scenario. Owners of a backyard chicken farm get pretty regular egg production from their chickens. It seems that when the weather is mild, chickens produce 11 eggs per day. When the weather is cold, chickens produce only 5 eggs per day. When it is hot, the chickens produce 9 eggs per day. About half the year is mild in this location, with cold days only accounting for 10% of the total. So we want to find the probability model for the daily egg production. All right, this is a random variable. We don't know on any given day how it's going to turn out. Now we've got a few different outcomes. So what are the outcomes here?
They produced 11 eggs in a day.
Okay, so they could produce 11 eggs in a day. What are the other outcomes?
5 and 9.
5 and 9. There we are. And we can pretty quickly figure out the probabilities of this too. What's the probability of getting 11?
Point 5.
0.5. So we can see, and if you weren't sure where we got that, it says about half the year is mild in this location. So we're just going to use half as our probability. So 0.5. The probability of only getting 5 eggs is going to be what?
0.1.
0.1, which means the last one right here will be 0.4. We've got a probability model, and now we can go ahead and plug that into our calculator, and let's find the expected value and standard deviation for egg production. And if you did forget, you need to create list stat edit. Just plug in these outcomes and the probabilities. I will go ahead and write this down real quick. So I'm going to call this random variable X. We can name it whatever we want. And so I'm going to create another one in a minute, which will have a different name. So random variable X, that it has an expected value and a standard deviation. And you guys can fill that in on our presentation. So we got 9.6 and 1.8 for those two parameters for this particular random variable. And that's all good. Hopefully we're feeling good with that. We've been doing probability models for a few days. So, hopefully that's almost second nature at this point. So this is one random variable. We could modify this, and we're going to see an example later where we can actually do the kind of stuff we were doing on Friday, where we are, what's the word I'm looking for? Where we are transforming the data by doing what we talked about a minute ago. But now we're going to look at something a little different. And I will erase this probability model, so make sure you have it written down in your page, but I'll leave it there for just a second. When they are putting eggs in the carton, the chicken wranglers have good days and they have bad days. If they break the first egg they package, there's a 65% chance they're going to break another. If they don't break the first one, there's only a 30% chance they'll break an egg out of the remaining day's production. And there's a 25% chance that they break the first egg on any given day. So I'm about to erase this probability model because we're going to need to do some more work. So, all right, I'm erasing it now. Now, before I create a probability model, we need to figure out, well, let's start it this way. I'm going to try and squeeze this all in. So I'm not going to make this one as big. I'm going to call this random variable y, first of all. And we'll look at the probability of different outcomes. So at the end of the day, what are the outcomes from this scenario? We're talking about breaking eggs. So what are the outcomes here?
So if you break the first egg, that's a 25% chance.
Okay. So in that
And then-
scenario, oh, go ahead.
I was just kind of gonna say the rest. You if you break that egg, then there's a 65% chance you'll break another one. But if you don't, there's only a 30% chance.
Yes. And you're on to something. Those aren't exactly the outcomes. That is what leads us to our outcomes. So at the end of the day, when we're looking back, or when these people are looking back on the work they've done, what are the possible outcomes they have as far as breaking eggs?
An egg breaks on the first day.
So they could break an egg. What does it seem like the possible number of eggs are that they could break?
Two
Two? They could break 2 eggs.
or more.
Well, in our scenario, we set it up simply. If I made it where they could break a lot of eggs, that would really complicate what we're about to do. So we're simplifying this.
Okay. So these are really good chicken wranglers, apparently.
Yeah, and they're also dealing with very few eggs, so there's not as much
Okay.
chance to break. How many other eggs could they break?
1 and 0.
1 and 0. There we go. So just so we have it clear, we did a random variable x that said how many eggs are produced. We don't know, but we know on average how many are going to be produced each day and the standard deviation. Now we're saying how many eggs are going to be broken while they're packaging them. It could be 0, it could be 1, it could be 2. All right, we're still fine with this. But now we need to figure out what these probabilities are. And maybe we can do this. Maybe there's a simple way of getting this done. We're still gonna have to do some math here, but maybe let's start with, okay, I'm not finishing any thoughts yet. Which one's the most complicated probability to figure out?
The middle one.
Yeah, that middle one will always be the more complicated one because it's not breaking the first egg and breaking the second, or breaking the first egg and not breaking the second. So we have like 2 different scenarios. So maybe we could look at the outer 2 possibilities. How do we find out the probability of breaking 2 eggs?
Is it 0.25 times 0.65?
There we go. Now, what this really is calling for, and I was kind of avoiding it, but I mean, maybe it's actually a good idea to go into it. This is really calling for a tree diagram, and hopefully you guys are already aware of that. So we could do the first egg breaks or doesn't break. And then from there, I'll just call this B sub 1. Then we could break a second egg or not break a second egg. Break the second egg or not break the second egg here. So I don't necessarily like this notation I picked, but if you can follow along with that. So B complement means we don't break. All right. So yeah, there's a 25% chance. So that's why Lily just said multiply 0.25, which is we have a 25% chance we break that, times if 0.65, because this is how we get 2 broken eggs. We break the first one, we break the second one, or another one. So there we go. If we multiply that, what is the 0.25 times 0.65?
0.1625.
0.1625. This is the only way that we can break 2 eggs. So I'm just going to write that down. 0.1625. Thank you for that. Now let's figure out the probability of breaking 0 eggs. What do we multiply there?
0.75 times 0.7.
There it is. Notice it is only a 30% chance that they break an egg. So this would be the 30% chance that they do break a second one. Here would be 0.7 that they don't. So go ahead and tell me 0.75 times 0.7 is
0.525.
0.525. All right. Now we can figure out the other ones by multiplying this scenario out and this one, and it's certainly a good idea to do so. We could also figure out this one by doing what?
Just taking the difference of the other two.
There you go. Let's add those two up, and whatever remains out of one has to represent the probability of breaking one egg. So you guys can tell me what that is.
.3125.
There it is. So this one, this is getting some practice with some of Unit 5 probability and tree diagrams. But now we have a probability model. We could break 0, 1, or 2 eggs, and that's a probability. Now we can figure out, very straightforward. Okay, well, there's a probability model. Now we can figure out the expected value and standard deviation. Let me put that down. This is the expected value of random variable y. And now we want to get the standard deviation of y. So there we go. We can see that on average, over the long run, we would expect to lose about 5/8 of an egg any given day. Of course, that could fluctuate. By any given day, it could be 3/4 of an egg more or less than that. And that kind of doesn't make sense when you talk about negative eggs, but it just goes to show the variability in the data. Okay, so we've got 2 random variables. And if you guys haven't written that down, I will leave that up for just another minute, because this is about to get really weird. And luckily, we're going to find some ways of not having to go through this much of a process as we move forward. And this is kind of the routine that we develop, right? Where we do something a long way and then we see that there's a shorter way of getting it done. So that's what we're doing for today. So the question is basically, how many eggs are produced and safely packaged for selling on any given day? So we need to find the probability model for successful egg production. And that's the production that we have minus our losses. Now you have those numbers written down, and I'm going to clear this screen now. And if I recall correctly, we've got, well, I need to write down our previous models. This is actually going to make the most sense. All right. So I'm going to do this kind of small. We could have gotten 11, 5, or 9 eggs with a probability of 0.5, 0.1, and 0.4. We also have random variable y, which is our losses. And we could have had 2, 1, or 0 eggs lost. And now it's going to be, let's see, it was 0.1625, 0.3125, and 0.525. So if I made a mistake on any of those numbers, you can point that out to me. I think that's right. So at this point, we're actually going to combine these two together. We're not actually looking at those summary numbers yet. We're going to come back to those in a minute. So let's not worry about the expected value or standard deviation, but let's figure out, after you take your production for the day minus the losses, what is the probability, or what are the different outcomes? Let's focus on that. So this is going to be x minus y. And these are my outcomes. And then we're going to look at the probability for each of these x minus y. So let me start by asking this question because I'm not sure that you'll know exactly what to do. Maybe you do. What is the fewest number of eggs that we could possibly get on any given day?
Three.
3 eggs. Because if we only produced 5 and broke 2, the fewest that we might walk away with is 3. So on any given day, what are the other outcomes we could get?
Four or five.
4 or 5. There we go. We could break 1 or 0. And then
7, 8, 9.
7, 8, and 9. Yeah, because we're looking now at we produce 9 on the day, and then we break 2, 1, or 0. So 7. Maybe I want to give myself a little bit more space on this. 8, 9. And then what are the only other outcomes?
10 and 11.
10 and 11. So of course, this doesn't exactly seem like reality. We could definitely get something besides 5, 9, or 11 eggs on a day. We could break more than 2, but you can see that would really complicate our next step. So we simplified to model it. All right, so let's look at this. We've got all these different outcomes, and how do we figure out the probability of getting only 3 eggs in a day?
Is it 0.1 times 0.1625?
That's it. We take the probability of getting 5 eggs times the probability of breaking 2 of them. And we're assuming independence here. That's an important assumption, but that's going to be an assumption that we use. So we can just multiply it out. So in this case, 0.1 times 0.1625, 0.01625. And we can, do we need to do another one, or do you kind of feel like you could fill in the rest of this table? Well, let's just do one more just to make sure, and maybe you don't need it. But what about, let's just do let's just go up to the max. So 11 eggs. What's the probability of getting 11 eggs? What do we do to find the probability of getting 11 eggs?
Point 0.5 times 0.525.
There you go. Probability of producing 11 and breaking 0. Multiply those together, and we get that. So you guys can, if you get the idea, you can start filling in this table. One of these is going to be a little bit trickier, and you'll probably figure out which one that is very soon. But I'm going to pause the video, let you guys fill in this table. So this is very good. I just ran through the numbers myself just to, make sure that it checks out all the same with me. This is all good. Now, the one that's a little bit weird, a little bit more challenging is number 9 right here. Why is number 9 a little bit more challenging?
Because there's 2 ways you can get 9.
Very good. There are 2 ways. We could have 9 produced with no breakage, or we could have 11 produced with 2 eggs broken. So this is actually a combination of 2 probabilities added together, and that is the answer I got. The one thing I'm going to do, just in case you guys didn't get these calculated yourself, I'm just going to add in the precision here. So this is 0.525, that's 0.6. Okay, that one's, number 7 is good. Number 8 is good. So I just got 2.5 added to the end of that one. And then that's also 2.5 right here. And that last one is good. Okay, so if you have this probability model, this is going to take a little bit longer to put into your calculator, but now you have one more probability distribution you can put in, and you can find the expected value and the standard deviation for successful egg production. All right, there it is. And your numbers might be slightly plus or minus a little bit if you did rounding on your probability model. And I know you might still be plugging the numbers in. So I encourage you to just finish that up and you can just double check. So those are basically the numbers that I have on my calculator as well. All right, now I started off this way, but I want to remind you, you are not going to have to set up a big probability model like this every single time you have multiple random variables that you're combining, because that would take forever and it would get super, super complicated. So this is just to illustrate the point. All right, so let's move on to the next page, unless someone has any questions you want me to pause here. All right, and I'm going to clear this because you can see I already have all these numbers on the screen. So let's look at this real quick. We just combined these, and when we combine, that can mean we could add random variables together. We could subtract random variables. In this case, we subtracted them, but I chose subtraction here to illustrate the point. All right, so we'll call initial egg production X and lost eggs Y. That's what we did before. And we've got these same summary numbers that you guys already have probably written down on a piece of paper there. All right, so let's first of all figure out when we subtracted X from Y, or sorry, Y from X, how did that affect the expected value? Look at those numbers, see if you can figure out the relationship there. So with expected value, this is always going to be the easier thing. And you can see right here, when we combine, it's just very straightforward. If we're subtracting X minus Y, then we just take the expected value of X and Y and subtract the expected values. And that's exactly what we got there. So it might not be immediately obvious, but if you plug it in your calculator, it's confirmed. This number right here is just 9.6 minus 0.6375. All right, so we could maybe think of it this way. The expected value of any combined variables, or let's go with this one specifically, X minus Y is going to be the expected value of X minus the expected value of Y. All right, nothing too complicated with that. It takes a little bit of looking at, but once you figure it out, it's a very straightforward relationship. But what's going on with standard deviation? And I'll just give you a second to look at that, see if you have any thoughts on it. If you read the chapter, you probably have some thoughts on it. So this is not a very straightforward relationship. I can't just add these together. If I add these two up, it does not equal 1.948. If I multiply them, no matter what operation I pick right here, you know, I can't multiply. Even dividing, that could be a possibility. So let me divide 1.8 by 0.746, and that doesn't work either. So nothing is really working here. Oops, that's not what I meant to do. So now let's look at this. We're adding the variances, and that's the key thing. And this is why we talked about variances to begin with and why it's coming back. Variance is simply the standard deviation squared. So we're basically doing this. And now let's try and figure this out. So my standard deviation, 1.8, if I square that to get the variance, so that's going to be variance of this. Well, 1.8 squared, just math real quick, that's 3.24. And this is rounded, but it'll be close enough for our purposes. I'm going to do 0.746 squared, and that's 0.5565. All right, so if I add these up, that gets me 3.7965. That's where I'll round it there. And I'm going to take the square root of that because this is the variance, the combined variance. So if I take the combined variance and take the square root of it, that gets me the standard deviation. So let's make sure that works. The square root of that number is, so 1.948. So this is our equation that we're using. And the kind of the shorthand way of talking about that is saying we're combining the variances. The square root is only here so that at the end we can convert all the variances back, the combined variances back into a square root. Now, another thing I want you to notice, and I think I'll talk about this more later, notice it doesn't matter whether we're adding or subtracting. When we were finding our expected value, we subtracted y from x and we got our final answer. But here I'm adding. And we're going to talk about this more, but I just want to make sure it's really important that you understand we always add the variances. Okay. So this is called the Pythagorean theorem of statistics. And you should know your Pythagorean theorem well enough to know that we're essentially just using that. Now, to be fair, we can combine a lot of variances together. This could theoretically be even more. The variance of z and the variance of a, random variable a, and so on, dot, dot, dot. It doesn't just have to be two. We could combine lots of things together. But, you know, sometimes, a lot of times we're just dealing with two random variables. And there's the main thing, always add the variances. So the question you might be having is, why are we adding the variances when we're subtracting the random variables? And hopefully you can follow along with the thought process. But your variance and therefore your standard deviation represents the uncertainty in the data, because it tells, well, we think it's going to on average end up here, but it could spread out from there. Each individual data point could be plus or minus a certain amount, right? There's uncertainty. So if we have multiple random events we're combining together, there's more and more uncertainty. So the egg production had a certain amount of variation. And then when we subtracted, that also had variation. So we're combining those variations together. And the overall successful egg production can go as low as 3 and as high as 11. That's a much wider range of possibilities. So there's more variability. Okay, and that's essentially the main idea behind it. So we always add variances. And so now we can come back to this type of question, the one that we ended with on Friday. And I said, it's probably not going to come out the right way because, and we're going to see kind of the distinction here. I'll talk about it now. But when you see 3 times x, this is not rescaling the data by a factor of 3. This is assuming you actually have 3 different random variables that are multiplying out. And I will say I typically don't like it when they give questions like this because it doesn't give enough context to really pick out what's going on. So maybe if I go and check the textbook right now, maybe this one does work out perfectly just by multiplying by 3, but I seem to recall this being a problem before. But anyways, we could look at this at 2 different ways. It could just be, hey, I want to rescale this. Like, and if we go back to going on Friday, here's my random variable x, the mean and the standard deviation. If it's 3 times the expected value of x, then that's just 3 times 80, which is 240. If it's 3 times the standard deviation of x, then that's just 3 times 12, and we get 36. So if it's rescaling the data, then that should work out just fine. But we can contrast that with this one down here, where it's x of 1, x of 2, x of 3 all added together. And you'd almost think, oh, that's just the same as 3 times x. So I could just get these same results. but it's not the same. We have multiple events. These are 3 different events of random variable X, and we will get, in this case, we have to use our Pythagorean theorem of statistics, that is. So if I want to find the mean of this, I can just add these 3 means together. The expected value, or the mean, is always going to be the same. So it's going to be expected value for x sub 1 plus the expected value of x sub 2 plus the expected value of x sub 3, which is going to be 80 plus 80 plus 80, which is 240. All right, really nothing has changed there. But we have 3 random variables. And I'm going to combine the variances of all these. So when I want to find the standard deviation of x sub 1 plus x sub 2 plus x sub 3, I have to do the combined variances. So I need to do the variance of x sub 1 plus the variance, and notice when I'm saying variance, I'm doing the standard deviation squared of x sub 2 and the variance of x sub 3, which in this case will be the square root of 12 squared plus 12 squared plus 12 squared. And we can figure that out. I'll just plug it at this point into the calculator to get that answer. And this gives me 20.785. So the main takeaway, and I know this might be some confusing math. We're going to go through some examples for the last part of class. But the main takeaway is that we have to consider, is this data being rescaled, and therefore I just multiply the standard deviation by a constant? Or is it multiple instances of the same event happening over and over? All right, so let's kind of put some context on this. Like I said at the beginning, I don't like these types of questions because there's no context and it's hard to know what the intention of the question asker is. But now with this question, we have some context. A company selling vegetable seeds in packets of 20 estimates that the mean number of seeds that will actually grow is 18 with a standard deviation of 1.2 seeds. And you buy 5 different seed packets. How many bad seeds do you expect to get? What's the standard deviation? All right. So it looks like the expected value for any one given packet is we will get 18 good seeds, which means we're going to have the expected value of bad seeds. I'll just call this random variable x. So the bad seeds, there should be 2, right? That's not a big stretch to understand that. Standard deviation of 1.2. So so if we're talking about good seeds, how about this? Let's just work with the 18, just because I want to make sure that I don't get confused as we go through it. We'll just work with the good numbers that they gave us, and we'll figure it out from there. Standard deviation of 1.2 seeds. So the standard deviation for this random variable is 1.2. So we will figure out how many good seeds we could expect out of 5 times 20 out of 100 seeds. And then we'll just kind of figure that out from there. Okay, so how many bad seeds do you expect to get? All right, if I'm buying 5 different packets, this is 5 repetitions of the same random event. So I'm not just multiplying this by 5. That would give me a wrong answer. Instead, what I'm going to do is I'm going to do the expected value of x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 plus x sub 5. I will say that that's kind of redundant to write. You could just do expected value of 5 times x as long as you understand that we're saying that we're repeating this 5 times. In practice, this doesn't make a big difference. It's just gonna be 18 times 5, which is 90. We would expect 90 good seeds, so therefore 10 bad seeds. Okay. Now that's not the hard part, because the next one is the standard deviation for this is going to be, like we saw before, it's the square root of this variance, all the variances added together. So it's going to be 1.2 is the standard deviation squared plus 1.2 squared plus 1.2 squared, and I'll write it out. And what I could do is think of it this way: 5 times 1.2 squared. And that would be a little bit easier for me to kind of answer that question. All right, so there we go. So is that right? 2.683, you guys getting the same thing? Okay. So this is combination of variances. And notice in this case, we are adding the random variables, but we are also, sorry, I lost my train of thought for a second. We're adding the random variables as opposed to our last example where we were subtracting the random variables, but it doesn't matter. It never matters. We're always adding here with the standard deviation. Okay, so this, there we go. I was just looking at the questions here. So if we look at part C, it says, what assumptions did you make about the seeds? And do you think this assumption is warranted? What assumption did we make here? Okay. So this is kind of like a hidden assumption perhaps, but the assumption here is that these are all independent, and that, you know, the probability if we had a lot of bad seeds in one packet, that doesn't have any impact on the amount of bad seeds we have in the next packet. And in this case, is it a fair assumption to make? What do you think?
Yeah, I think so.
Okay. It kind of depends on if you got 5 different types of seeds, each that had 20 and each had the same statistics on them, then that might be a fair assumption. If you got 5 packs of the same type of seed, maybe there's a possibility they were all packaged at the same time, and maybe it was just a bad batch. So there are situations where it might not be a safe assumption to make, in which case these numbers are no longer accurate. But if we do assume that these are all independent and one has no impact on the other, one probability, then yeah, there we go. Our calculations are good. All right. I want to be careful with which ones I go through here because, oh yeah, we need to cover a little bit more. But I have a number of example problems, and there's 2 in particular I want to go through, and I'll make sure we have time for that. So we've been looking at discrete random variables, and we talked about that. Discrete meaning that there are only specific outcomes it could take. Anytime we create a probability model, we are enumerating all the possible outcomes like we did at the beginning with all the different number of eggs we could end up with. But with continuous random variables, the random variables can take on any value in a particular range, and we can think of what continuous variables could be. So there's a few examples right there. Now, this is, I say a little simpler, hopefully simpler for you, because when we're working with continuous random variables, we're just using the normal model, all right? So that might or might not be good news for you. You might hate having to go back to the normal model. This is going to be with us the entire rest of the way. So get comfortable with it, sooner the better. If you have the mean and the standard deviation for the model, then we have everything that we need. All right, and so now I wanted to run through a few examples of this. I might actually do, let me do this. Yeah, let's just do this one. I'll skip the next one. Historically, so this is a television fundraiser that some people donate different amounts of money. Okay, we get that idea. Historically, pledges are about 32 with a standard deviation of 54. If 120 people call in pledges, what are the mean and standard deviation of the total amount raised? What assumption did we make in answering this? Well, let's answer part A first of all. So we've got 120 pledges coming in. We could answer the first part, the expected value. So this is a continuous variable, right? So the expected value of this continuous variable is $32. So if we get 120 pledges, how much money do we think we're going to get on average?
Whatever 32 times 120 is.
There we go.
38.40.
38.40. So I can just do the expected value, and I know this means that we had 120 people give us, or this organization, a pledge. Anyways, I'm just getting to this. Okay, $3,840. Now with the standard deviation, remember, this is 120 different events. We're not scaling by 120. We're saying we have 120 events. Each of them have their own uncertainty because we don't know that we're going to get 32 for each of these pledges. They could all be really low. They could all be incredibly high. You know, that would be great. So how do we figure out the standard deviation of this new model? Any thoughts yet? So I remind you of that idea. Did anyone already come up with an answer? You can just share what your answer is if you have one. So you came up with what I agree is the correct answer. How did you get that?
Sorry, what did you say?
I was just saying, I liked your answer. How did you come up with it?
I took 54 and then squared it, and then I multiplied it by 120, and then took the square root.
There we go. 120, we have 120 different events of a variance of 54 squared. So I'm going to take that 54 squared, multiply by 120 because of the 120 people that called in. And once I get that total number, which is quite big, I can take the square root of it. And this does give me let me put it in units, $591.54. So we would expect the standard deviation of this, our normal model, is going to be 3,840, but it could fluctuate by a factor of 591.54. Now that makes it look, you have to be careful about this. So I'll just write it that way. So there we go. Now, the assumption that we made in answering this question was what?
The people who give money are all independent.
There we go. We have to assume that these were not just a bunch of rich people who got together and 120 really rich, wealthy donors called, or that 120 people who only donate like $1 or $2. So we're just going to assume it scatters and it's representative sample. So there you go. It's independent. Okay. So with the time that we have, I could do some more. And if some of these, if you look through this presentation, you might see some that you really want to go through that we just don't have time for today. I wanted to look at, let me see. I know I wanted to look at problem 44. So let's start with that one, and then I'll go and pick one other one to look at. Okay, so I skipped over 42, but in 42 we have a bike shop. Okay, so that's the only important thing. So they're going to be having a sale, a sidewalk sale. And they have a basic model bike that sells for 120 and a deluxe that sells for 150. Past experience indicates that sales of the basic model will have a mean of 5.4 bikes and a standard deviation of 1.2. And sales of the deluxe model will have a mean of 3.2 with a standard deviation of 0.8. Cost for setting up the sidewalk sale is $200. Define the random variables and use them to express the bicycle shop's net income. Okay. So this one I wanted to go through because it has pretty much all the different concepts that we talked about rolled into it. And maybe the first thing that we want to do is we can scale this data first. So this is an example where you look at it. If we are changing the units, then this is an example of where we would scale the data differently. So notice that I'm going to start by converting this 5.4 bikes with the basic. This is basic model. So let me make sure that's very clear. The basic model has a mean of 5.4 bikes, and it costs $120. So I want to convert this from the unit of bikes into the unit of dollars. How many dollars is this? Are we making from the basic model? And this is one that we can very much just, let me see, there's basic and deluxe. So I'll call this random variable B for basic. So the expected value is just going to be, and let me actually clarify this a little more. I have $120 times my random variable B. So this is going to be just 120 times the expected value of random variable B, which is just 120 times 5.4, which gives me $648. Now, this is not multiple events. This is rescaling by changing from one unit to another. So when I look at the standard deviation of this, 120 times random variable B, all I have to do is multiply this out. So hopefully you can see the difference. In the previous examples we were looking at, we had multiple seed packets. So we had to combine the variances, or we had multiple donations. So we had to, those were multiple events. This is not multiple events. This is just changing it from bikes sold to dollars earned from the bike. So we're changing units. So now I can just do this 120 times the standard deviation of B, which is going to be, standard deviation is 1.2. So I'm going to do 120 times 1.2, which gives me $144. All right, and I can do the same thing for the advanced bike. So I'll do that pretty quickly. I'm just going to do 150 times each of my variables. So it's going to be expected value of 150 times deluxe. So it'll just be 150 times, how many deluxe bikes are we going to sell on average? 3.2. This becomes 480. And we can do the last one for the standard deviation. Got 0.8 is a standard deviation, so it's going to be 150 times 0.8, which is going to be 120. All right, so I wanted to start by rescaling. All right. And now I've got two random variables. So let me kind of show it this way now. The expected value for basic bikes is going to be 648 with a standard deviation of 144. The expected value for deluxe bikes is 480 with a standard deviation of 120. So if I want to combine these together, because I'm going to sell deluxe and base, I keep saying I, but it's whoever's in this example, but we're going to sell 100 or a random amount of bikes, but we might expect this much profit. So I'm going to combine B plus D. And now it's just going to be the expected value of basic bikes plus the expected value of deluxe bikes. Is this your favorite stuff we've done in statistics so far? It's got to be up there, right? Luckily, remember with the expected value, that's really straightforward. We just straight up add them together. So 648 plus 480 is $1,128. All right, and now we can get the standard deviation of B plus D. What do we do to get our standard deviation? Well, let's run through this. Hopefully with this example, we can understand a little better. This is just that Pythagorean theorem of statistics. If we have multiple standard deviations that we're trying to combine together, we have to combine the variances instead. So I've got the standard deviation for basic bikes and a standard deviation for deluxe bikes. I have to combine these together using that Pythagorean theorem of statistics. So that's my calculation. And maybe you guys were doing that at home. You just didn't know how you wanted to say that out loud. But when I do this, it's 187.45. So $187.45. All right. Is everyone good with that concept? Okay, got some thumbs up on that one. All right, and I know this is confusing to start off with. So remember, your test isn't until next Monday, so you're gonna have some time to absorb this knowledge. So let's see. The standard deviation of net income. Okay, well, we're not completely done yet. So the last thing to consider is that there's a cost of setting up for the sidewalk sale, which is $200. So we need to figure out how that factors in. So let's first of all find out the mean. What's the mean of the net income here? What will we do to get that? So let me ask this question. If we are typically earning $1,128, are we really walking away with $1,128?
Would you have to subtract the $200, the expenses?
There you go. We had to subtract our cost for setting up the sale. So if we subtract that, that's pretty straightforward. That's going to make it $928. So this is another sort of transforming the data. This is not a new event. This is just a constant amount that we have to subtract away, because the idea is if we did this sale hundreds and hundreds, thousands, millions of times, whatever the case, we're going to always subtract $200 from whatever we earn. So that's going to be a constant that we take away. Does that affect our standard deviation?
No.
No, it will not, because the standard deviation is the spread of the data. And so that shifting of $200 is basically, remember, like taking this distribution and shifting it down by 200. But the spread will stay the same. So now we can say that our standard deviation here is $187.45. The mean, once you've factored in the $200 loss that we have to take every single time, is, there you go, it's 928. All right. And of course, we've answered this a few times. Did we make any assumptions here?
The sales of bikes are independent.
Yeah, that's essentially it. So, if we sold a lot of deluxe bikes on one day, we have to assume that does not have any impact on the amount of basic bikes that we sell, and vice versa. You can determine for yourself if that's a fair assumption, but it's the one that we're going to roll with. And there we go. We have our model. So if I was going to create a model, a normal model, it would have a mean of 928 with a standard deviation of 187.45. And we could then use that to answer some other questions. And there's just not time. I might start off tomorrow with going over another question like this, and it probably wouldn't hurt us to see some more like this. So let me call that a day, and we will look at some more of this tomorrow before we jump into the next lesson. All right, so if you did want to see some more, feel free to stick around if you had some questions you wanted to clarify. Besides that, I'm going to call that good for the day, and you can have a wonderful day. I'll see you tomorrow.